Hi, my name is Bartio van Blokland, and together with Theoharis, we've written this paper, an indexing scheme and descriptor for 3D object retrieval based on local shape querying. Let's get right into it. The paper itself presents three main contributions. We'll take a look at each of these contributions in order, starting things off with the Quickie shape descriptor. But as you may be able to notice, what you're looking at here is not a more conventional style PowerPoint presentation, because I realized that going through that route would also mean passing up a great opportunity to have some fun. So, if you'd be so kind to get up from your chair and follow me up the stairs, I thought it'd be much more interesting for all of you to skip straight past all the diagrams, equations, and lots of text, and explain the descriptor by showing it in action. Oh, crud. I probably should have turned on the lights before heading up here, shouldn't I? One moment. There we go. Sorry about that. Anyway, this is my plane, and I'll just go ahead and put this cylinder into the scene. Now this cylinder is the support volume of the Quickie descriptor, and I can move it around, like so, and also rotate it, like so. And when I move this thing in the vicinity of the plane, such that it starts to intersect with its surface, you can see that there's images being produced in the bottom left. Now of these images, the left one is the Quickie descriptor, and the right one is a grayscale version. I'll get back to you how both of these are being generated. To do so, let's take a look at the nose of the plane. Now if I move the cylinder over here, you can see that the images in the bottom left closely resemble the shape of the nose itself. However, the reason why is not very easy to see in this way. So let's first reduce the resolution of the image a little bit. What you can see here is that the support volume consists of a stack of layers, where each layer contains a number of circles with increasing radii. These circles subsequently intersect with the surface of the object. Computing a Quickie image is nothing more than taking a pair of circles on the same layer, for example these two, and computing the number of intersections between the object surface and each of those circles. You can see the raw intersection count in the grayscale image on the right. If the number of intersections is different, a Boolean value of true is produced and otherwise false. This process is repeated for each pair of circles in the support volume, resulting in a binary image. To visualize the generation process further, let me take a different camera perspective here. The procedure I just described is mostly similar to folding up an object around the primary axis of the cylindrical support volume, as you can see here. When I now leave the plane in its folded up state and move the support region around, notice how the shapes of the shown images closely resemble those you can see in the flattened object. The plane object also looks rather weird in this way. In the paper, we present three main advantages of the Quickie descriptor: its resistance to clutter, the descriptor being binary, meaning it doesn't require much space in memory and on disk, and its generation being quite inexpensive. There are, however, two questions I would like to focus on in more detail. Specifically, how does it achieve its resistance to clutter, and how its resistance to clutter is evaluated in the paper. We'll start with clutter resistance, and for that we'll also be returning to the demonstration stage. Let's look at the nose of the plane again. When I put the cylinder support volume here, you can see in the bottom left that the images are similar to the ones that we've seen before. However, let's add some decorations to the plane this time. Let's say maybe some headlights. Ah, great. Now, if I return the cylinder to where it was before, you can see that there's now a bunch of additional detail there. The important thing here is that as I turn the headlights off and on, you can see that the nose cone shape is still preserved in the Quickie image, even though there's now a whole bunch of additional clutter in the neighborhood. This is the primary reason that the images are clutter resistant. We've also tested the effects of clutter on the matching performance on the Quickie Descriptor, as well as several others. The clutterbox experimental procedure we used was not proposed in our paper. However, since its rather recent introduction, we felt it was useful to go over in detail. So the first thing that we need is a set of random objects. Let's say 10 of them. One moment here. This one, and yeah, this here looks pretty good. Now, the next thing that we need to do is to ensure that all of these objects are of uniform size. So we'll be fitting them inside of unit spheres, like so. The main idea behind the clutterbox experiment is to select an object at random, let's say this one, and determine to which degree a given descriptor is able to locate each vertex of that object in a scene consisting of the object itself and a varying number of clutter objects. The experiment therefore starts by generating one descriptor for each vertex, after which it assigns a random orientation to all chosen objects. After that, it attempts to locate each of the initially generated descriptors in a scene, with initially only the object itself, but followed by scenes with an increasing number of clutter objects. So that was the Quickie descriptor. Let's now take a look at the next main contribution, the Hamming tree indexing structure. So in the previous section, we have seen how we can generate Quickie descriptors from 3D objects. Let's now say that we take 12,500 of those objects and generate descriptors for each of their vertices. Obviously, that will create quite a few of them. In fact, it's 828.5 million. Now, it would be interesting if we were be able to take one of these Quickie descriptors and try to find the most similar images in this dataset. This is exactly the problem which the Hamming tree indexing structure attempts to solve. The Hamming tree is a data structure intended to locate sequences of bits whose Hamming distance is closest to a given query bit sequence. In our case, those bit sequences will be Quickie descriptors. We'll get into how this tree works in a moment, but first we need to make two observations underlying the design of the tree. The first one relates to being able to compute a minimum Hamming distance between two bit sequences. For example, let's consider these two bit sequences with random bits. Now, without knowing exactly where the bits are within these sequences, let's say that sequence A has 250 bits set to 1, while sequence B has only 200. At this point, we know that wherever the bits end up being, the minimum Hamming distance between these two sequences must be 50. The second observation is the possibility of using the rough distribution of bits within a sequence as a heuristic for locating similar neighbors. To illustrate what we mean by this, consider this bit sequence. We can subdivide this sequence into equivalently sized chunks, and subsequently count the number of bits set to 1 in each of those. When two bit sequences are similar, the number of set bits within each chunk should be similar too. With these observations in mind, we can proceed to introducing the tree's construction, as well as an algorithm for querying its contents. Let's start with the Hamming tree's construction. And for that, we'll quickly return to the example we saw before. When the tree indexes a new bit sequence, it starts by subdividing it into smaller chunks, just like in our example. The primary mechanism for creating the tree consists of removing the first chunk at each level in the tree and looking at the number of bits set to 1 in the remaining sequence to determine which next branch to take. Let's show this process with an example. At the top, we have the first level of a Hamming tree with all 17 branches, as our bit sequences are 16 bits in length. At the bottom, we have the previously computed bit counts. Now in total, there are 10 bits set in this bit sequence, which means we'll pick the 10th branch here to proceed to the next level. Moving down a level, the next thing we need to do is to remove the first chunk from our bit sequence. This leaves us with a total of 7 set bits, which means we'll now take the 7th branch down. This procedure is used for determining which branch a particular descriptor should be placed when it is inserted, which for the construction of the algorithm only leaves the question of how the tree is expanded over time. At this end, a Hamming tree consists of two different kinds of nodes, intermediate and leaf nodes. Intermediate nodes contain references to intermediate and leaf nodes, but do not contain bit sequences themselves, while leaf nodes only contain bit sequences. At the start, a Hamming tree consists of a single intermediate root node and one leaf node for each possible set bit count the bit sequences being indexed can have. Inserting a node into the tree is therefore done by navigating the tree until a leaf node is encountered, inserting the bit sequence into it, and if the number of sequences contained in the leaf nodes exceeds a set threshold, the leaf node is converted into an intermediate node and its contents are distributed over its children, thereby expanding the tree dynamically. So that is how a Hamming tree is constructed. Let's now briefly look at how it can be queried. The querying mechanism iteratively selects nodes to visit depending on their minimum Hamming distance to a given query. As we've seen before, such a minimum distance can be computed based on the number of bits set to 1 in a given sequence. In this example, selecting the branch of 7 here would incur a distance penalty of 3. And that concludes the Hamming tree indexing structure. We'll now move on to the final major contribution of our paper, the weighted Hamming distance function. So during the development of our implementation, while analyzing the search results returned by different query images, we noticed that there was a pattern occurring for some specific queries, specifically those containing a small number of bits set to 1. An example of such an image is shown on the left. Running this image through our Hamming tree resulted in the following search results. The top left image is the top result here, and subsequent results are sorted from left to right, with the worst results being shown in the bottom right. At first glance, the top results in particular seem to be very similar to the curves being queried. However, the same dataset these search results were retrieved from also contained this image. As you can see, here the Hamming distance ranking function evidently considers images which are rather empty to be better matches than an image which clearly contains the curves we're looking for. So what went wrong? Why is Hamming distance not selecting more desirable images in cases where the query image does not have many bits set to 1? Well, in terms of Hamming distance, the image on the right is a superior match to the query, so the algorithm is doing what it's instructed to do. Instead, the problem is Hamming distance being used in a situation where the query has a low number of bits set to 1. To explain this in terms of Quickie images, because the number of white pixels is low, finding images which also have those pixels colored white is much more important than finding ones with matching black ones. The Hamming distance function weights each of these discrepancies as equally important. However, the weighted Hamming distance function we propose in the paper argues that the occurrence frequency of each bit value also matters depending on the application it is used. The weighted Hamming distance function is nothing more than a mechanism to automatically weight each type of mismatch depending on the ratio of bits set to 1 in the query image relative to the total number of bits. This is a rough outline of the design of the function. The denominators are pre-computed based on the number of set or unset bits in the query, while the numerators compute the occurrence of each type of mismatch. The results of implementing this function in our retrieval pipeline are shown below. As you can see, the results are aligning much better with our query image. We also evaluate each distance function quantitatively and show the weighted Hamming distance function is better able to distinguish between relevant and irrelevant Quickie images. Unfortunately, while we have attempted to create an indexing structure which allows efficient retrieval using the weighted Hamming distance function, we have not succeeded at this, and present the best strategy we have found thus far as a negative result in the paper. And there you have it. This paper has presented 3 main contributions: the Quickie Descriptor, a fast, lightweight, and clutter resistant shape descriptor, the Hamming tree, a scalable indexing structure for binary data, and the weighted Hamming distance function used for ranking sparse descriptors. As a final note, we'd like to make you aware that the source code of everything we have presented is freely available in these repositories. It's worth noting that we spend a fair amount of time refactoring these to make them as easy to use as possible. We encourage you to use our work in your projects. And with that, we'd like to thank you for your attention.